Assalamualaikum and a very good day. My name is Muhammad Zairi bin Baharum from the Faculty of Mechanical and Automotive Engineering Technology, University in Malaysia, Pahang. So for this video, I will continue the topic of product design for manual assembly, the last part for this chapter. Yeah, for the DFMA courses, the design for manufacturing and assembly course. So in this lecture, we will learn about the parameters that influence the handling time and also the insertion time. Yeah, so two topics which are parameters which influence the handling and also the insertion time. Yeah, okay. So what is the effect of part symmetry on the handling time? So the assembly operations involve at least two component parts, which are first is the part to be inserted, and also the second one is the part or assembly receptacle into which part is inserted. The orientation involves the proper alignment of the part to be inserted relative to the corresponding receptacle. So orientation also can be divided into two distinct operations, which are the alignment of axis of part that corresponds to axis of insertion, and also rotations of part about this axis. Yeah. So and there are two kinds of symmetry for a part, which are the alpha symmetry and also beta symmetry. What means by alpha symmetry is depends on angle through which a part must be rotated about an axis perpendicular to the axis of insertion to repeat its orientation, while the beta symmetry depends on the angle through which a part must be rotated about the axis of insertion to repeat its orientation. So, continue talking about the effect of part symmetry on handling time. As you can see in the figure, there are the alpha and beta rotational symmetries for various parts. Yeah, the shape, rounded shape, also the rectangular shape. So a square prism that is to be inserted into a square hole would first be rotated about an axis perpendicular to the insertion axis. Since with such a rotation, the prism will repeat its orientation every 180 degrees, which is the alpha symmetry. And prism would then have to be rotated about the axis of insertion. And since the orientations of the square were to be inserted in a circular hole, it will have 180 degree alpha symmetry or 0 degree beta symmetry. Yeah, this is the table which show the value of the alpha and beta rotational symmetries for various parts. Time standard systems are used to establish the assembly times in industry. So several different approaches have been employed to determine the relationships between the amount of rotation required to orient a part and the time required to perform that rotation. So there are two most commonly used systems, which one is the methods of time measurement. We call this MTM system, and also the work factor, which is the WF system. I think the MTM is also related to the work study. If you are familiar with the work study method in the industrial engineering, yeah, there is a work study which we also use the MTM system, yeah, to determine the assembly time based on the sequence of the job that has been that is performed by the operator. Yeah. So what is the MTM system? Yeah, the MTM system is the maximum possible orientation is employed, which is one half the beta rotational symmetry of a part. So effect of alpha symmetry is not considered in the MTM system. So MTM system classifies a maximum of possible orientations into three groups, which are symmetric, semi-symmetric, and also non-symmetric. While the work factor system, the WF system, the symmetry of a part is classified by the ratio of the number of ways the part can be inserted to the number of ways the part can be grasped preparatory to the insertion. Yeah. For a square prism to be inserted into a square hole, one particular end first can be inserted in 4 ways out of the 8 ways it could be suitable grasp. Hence, on average, one half of the part's grasp would require orientation, and this is defined in the WF system as a situation requiring 50% of orientation. So account is taken of alpha symmetry and some account is taken of beta symmetry. So this is a figure of the classification system. You can see that a single parameter gives a satisfactory relation between the symmetry of a part and time required for orientations. So you can see the handling times for a different angle of symmetry. Yeah. So the total angle of symmetry is alpha plus beta. The shaded areas in the figure indicate the values of total angle of symmetry that cannot exist. The symmetry of a part can be conveniently classified into 5 groups. Yeah. The first groups, which represents a sphere, is not. Yeah. The first group represents a sphere is not generally of practical interest. So there are 4 more groups are just suggested that are employed in the coding system for part handling. So comparison of these experimental results with MTM and WF orientation parameters shows that these parameters do not account properly for the symmetry of a part. Yeah. So okay, we continue with the WF system. You can see the figure on the effect of a part thickness on the handling time. So thickness of a cylindrical part we consider as the radius. I think I mentioned this in the previous lecture. Yeah, thickness for non-cylindrical parts is the maximum height of part with its smallest dimensions extending from a flat surface. Yeah. So you can see how in the figure if you have how the thickness is defined for cylindrical parts. Yeah. And also you can also see in the graph shown next to the figure the handling time penalty given for those thicknesses for different kind of either it is a cylindrical or a non-cylindrical. Yeah. Okay, the definitions of the WF systems on the cylindrical parts. Yeah, cylindrical parts is a parts having cylindrical or other regular cross sections with 5 or more sides, while the non-cylindrical parts is the diameter is greater than or equal to its length. So parts with a thickness greater than 2 millimeters present no grasping or handling problems. Yeah. But for long cylindrical parts, this critical value would have occurred at a value of 4 millimeters if the diameter had been used for the thickness. So grasping a long cylinder of 4 millimeter in the diameter is equivalent to grasping a rectangular part of 2 millimeters thick if each placed on a flat surface. Yeah, so this is the condition. Okay, continue talking about the WF system. You can see in this figure the effect of the part size on the handling time. So you can see the handling time penalty for different sizes of parts, which are defined as a very small, small, medium, and large for cylindrical and also non-cylindrical parts. So a size of a part is the largest non-diagonal dimensions of parts outlined when projected on a flat surface. It is normally the length of the part. So parts as shown in the figure can be divided into 4 size categories, which are very small, small, medium, and large. So large parts involve little or no variation in handling time with changes in their size, handling time, while handling time for medium and small parts display progressively greater sensitivity with respect to the part size. Since the time penalty involved in handling very small parts is large and very sensitive to decreasing part size, so tweezers will usually be required to manipulate such parts. So tweezers can be assumed to be necessary when the size of the part is less than 2 millimeters. Okay, we see about the effect of weight on the handling time itself. So the effect of increasing the weight on grasping and controlling is found to be an additive time penalty, and the effect on moving is found to be proportional increase of the basic time. For the effect of weight on a part handled using one hand, so yeah, usually operators will work with two hands, but for the effect of weight on a part handled using one hand, the total adjustment TPW to handling time can be represented by the following equation. Yeah, so TPW is equal to 0.0125 times by the weight plus 0.011 of a W times by the TH. Yeah. So W is the weight of the part, TH is the basic time for handling a light part when there is no orientation is needed and when it is to be moved a short distance. Okay, so we see here the effect of a symmetry for parts that severely nest or tangle and may require tweezers, yeah, for grasping and manipulation. So a part may require tweezers when you have this condition. First, if its thickness is so small that the finger grasp is difficult, so you have a very small the part thickness is very small, so you cannot use your finger to grasp it. Second, if the vision of the operator is obscured and prepositioning is difficult because of its small size. A third condition is when touching it is undesirable because of high temperature, yeah, for example, and it's dangerous and fingers cannot access the desired location. So you can see in the figure, you may need tweezers if the thickness is so small, so your finger cannot grasp it and it's difficult to be grasped when your vision is obscured and the part is hot in temperature, and also the fingers cannot access the desired location, like in the figure when you would like to put the washer, yeah, in a hole before you can tighten the bolt and nut. Yeah, okay. And a part is considered to nest or tangle severely when an additional handling time of 1.5 seconds or greater is required due to this factor. So in general, two hands will be required to separate severely nested or tangled parts. Yeah. So operator need to work by using their two hands. Yeah. So helical springs with open ends and widely spaced coils are examples of parts that severely nest or tangle. So in general, the orientation using hands results in a smaller time penalty than orientations using tweezers. So therefore, factors necessitating the use of tweezers should be avoided if possible. Okay. Okay, now we will see the effect of chamfer, yeah? A chamfer design on insertion operations. Yeah, you can see in the figure A the geometry of the pack, and figure B is the geometry of the hole. So two common assembly operations are the insertion of a pack into a hole and the placement of a part with a hole onto a pack. So the dimensionless diameter clearance, which is C, yeah, between the pack and the hole is defined by the D minus D, the outer diameter, and the inner diameter divided by the outer diameter. Okay, so this graph shows the insertion times against the dimensionless clearance, the effect of the clearance on the insertion times. So you can see here the effects of a clearance for a design with no chamfers, chamfer on hole, chamfer on pack and hole, and also a curved chamfer. So the conclusion from this graph are, for a given clearance, the difference in the insertion time for two different chamfer design is always a constant. Yeah, a chamfer on the back is more effective in reducing insertion time than the same chamfer on the hold, while the maximum width of chamfer that is effective is in reducing the insertion time for both the pack and the hole is approximately 0.1 times D. And for conical chamfers, the most effective design provides chamfers on both the pack and the hold with W1 equals to W2 equals to 0.1 times the D, the outer diameter, and both the theta angle 1 and 2 are equal. And the manual insertion time is not sensitive to variations in the angle of the chamfer for theta angle between 10 to 550 degrees. And a curved chamfer can have advantages over a conical chamfer for small clearance. So these are the conclusions from the graph of the effect of clearance on the insertion time. Yeah. And in this figure, you can see the points of contact on chamfer and hole. Yeah, the long manual insertion time for pack and hold with a small clearance is probably due to the height of engagement occurred between the pack itself and the hole during the initial stages of insertion. So the figure shows the possible situations. Yeah, there are two possible situations which may cause difficulties during the assembly. You can see in the figure A, the 2 points of contact arising on the same circular cross section of the pack give rise to forces resisting the insertion. While in figure B, you can see that the pack has become jammed at the entrance of the hole. So these are two situations which may cause difficulties to your assembly. Okay, this is the figure of the chamfer of constant width. For a chamfer conforming to a body of constant width, the insertion time is independent of dimensionless clearance C in the range of C is greater than 0.001. So the curved chamfer is the optimum design for pack in hole insertion operations. Yeah, this is the conditions for the chamfer with a constant width. Okay. So what are the effects of obstructed access and restricted vision on insertion of threaded fasteners of various designs? So when the distance from the obstructing surface to the hole center was greater than 16 millimeters, the surface had no effect on the manipulations and the restriction of visions was the only factor. So under these circumstances, the standard screw inserted into a recessed hole will give the shortest time. For a standard screw with a standard hold, an additional of 2.5 seconds was required, and when the hole was closer to the wall, thereby inhibiting the manipulations, a further time of 2 to 3 seconds was necessary. The restriction of vision had little effect when access was obstructed, because the proximity of the obstructing surface allowed tactile sensing to take the place of sight. So you will use a tactile sensing to replace the functions of you need to see or the place of sight. So when the obstruction was removed, restricted vision could account for up to 1.5 seconds additional time. So in this figure, you see the effect of the number of threads on time to pick up the tool, engage the screw, tighten the screw, and also replace the tool. So as shown in the figure, the effect of the number of threads on time to pick up the tool, engage the screw, tighten the screw, and also replace the tool. There was no restrictions on the tool operation for any of these situations. For different types of threads like the slot head, Phillips head, Allen key, the Phillips head. Yeah. So this is the effect of obstructed access on the time to tighten a nut. Yeah, tighten a nut like using the open end wrench, the box end wrench, the socket wrench, hex nut driver. Yeah, the rundown time versus the clearance for different tools. Yeah. So as shown in the figures, the time to turn down a nut using a variety of hand operated tools, and where the operations of the tools was obstructed to various degrees. And it shows the penalties for a box, and from the graph we can see that the penalties for a box and wrench are as high as 4 seconds, yeah, per revolution when obstructions are present. This is the effect of obstructed access and visions on the time to insert a pop rivet. So the average time taken to pick up the tool, change the rivet, move the tool to the correct location, insert the rivet, and also return the tool to its original locations was 7.3 seconds. You can see in the bottom, figure A shows the combined effect of obstructed access and visions. So this is to show when your operator been faces obstructions both in the access and also the vision, the time penalty given for this situation, while figure B shows the time penalty given for the effects of obstructed access only. Yeah. So in the latter case, the time penalties of up to 1 second can be incurred, although unless the clearance are quite small, the penalties are negligible. Yeah. So with restricted vision present, much higher penalties on the order of 2 to 3 seconds were obtained. Okay, that's all for this lecture, which will conclude the third topics, the third chapter for these courses. Thank you for watching and listening. See you again. Thank you.